We stand upon a world. We think we know. A world of green fields, rolling hills, quiet gardens. But just beneath the surface, there is another realm entirely. It is a kingdom of darkness, pressure, silence. This hidden world is governed by its own set of rules, its own physical laws. It is a place where moving just a few inches requires immense effort and incredible strength. For most creatures, this subterranean landscape is an impassable barrier, a solid wall of earth that resists all attempts to enter. The sheer weight of the soil above creates a crushing force, making every movement a struggle against the planet itself. Imagine trying to swim, not through water, but through solid ground. The soil pushes back with unyielding pressure. Every particle of dirt, every tiny stone creates friction. To move forward is to fight a battle against the very fabric of the land. It is a challenge that seems impossible for any living thing to overcome. Yet, for one extraordinary animal, this is not a barrier. It is home. This creature navigates the dense, dark earth with an ease that defies our understanding. It has mastered a world that we can barely begin to comprehend, using a set of tools and techniques honed over millions of years of evolution. Here, in this freshly turned earth, we see the only sign of its presence: a small mound of soil, a miniature volcano on a peaceful lawn. It tells a story of incredible power, relentless industry. But what created it? What kind of animal possesses the strength to displace so much earth? The answer lies with a creature rarely seen, a master of the underground. It is a small mammal, often weighing no more than a few ounces. It spends nearly its entire life in complete darkness, carving out a complex network of tunnels, a hidden empire that spreads unseen just below our feet. This small velvety animal is the mole, and its life raises a remarkable question, a puzzle of biology and physics. How can such a small creature generate the force needed to push through dense, compacted earth? How does it breathe where there is so little air? How does it find its way in total blackness? The answer is not just about muscle, it is about physics. It involves leverage, pressure, ingenious biological machinery. In this film, we will uncover the hidden science behind this subterranean superhero, revealing the secrets of the superpowered mole you never knew existed. To understand the mole's incredible abilities, we must first look at its tools. This is not just a paw, it is a digging machine, a marvel of natural engineering. Look closely at this forelimb. It is short, broad, spade-like, and equipped with powerful claws. The entire limb is rotated outwards, permanently positioned for excavation. This orientation lets the mole shove soil to the side, rather than just scratch at it. It is a design that prioritizes power and efficiency above all else. Every bone, every muscle is optimized to move earth with maximum force and minimum effort. The challenge the mole faces is immense. The ground is not empty space. It is a dense material, a mixture of minerals, organic matter, and water. Pushing through it requires overcoming both friction and pressure. Think of it like this. Digging a tunnel is like trying to inflate a balloon inside a box of sand. The sand pushes back from all sides. To create a tunnel, the mole must exert a force greater than the resistance of the surrounding soil. For an animal of its size, this should be an impossible task. This is the central mystery we will explore. Our journey will take us deep into the science of this elusive creature. We will use archival documents, old scientific notes, and forgotten experiments that first began to unravel the mole's secrets. We will apply the principles of physics, using mathematics to calculate the forces at play. You will see the world from the mole's perspective, through advanced imaging and slow-motion footage. We will peel back the layers of fur and flesh to reveal the biomechanical wonders that power this animal. It is a story of hidden adaptations, a tale of how evolution has crafted a perfect digging machine. We will explore the trade-offs it has made, sacrificing sight for an unparalleled sense of touch, and an ability to navigate a three-dimensional world of tunnels. This is the story of how a small, unassuming mammal solved one of nature's greatest engineering problems. Join us as we dig into the physics of the mole and reveal the extraordinary superpowers hidden in the dark. To truly appreciate the mole's incredible feat, we must first understand the world it moves through. The ground beneath our feet feels solid, immovable. But what is it really? Soil is not a single, uniform substance. It is a complex and dynamic material. It is a mixture of tiny mineral particles, like sand, silt, clay. These particles are jumbled together with decaying organic matter, water, pockets of air. The exact combination of these ingredients defines the soil's character. It determines whether the ground is loose and crumbly or dense and hard as rock. For the mole, this composition is a matter of life and death. Imagine you are trying to push your hand into a bucket of dry sand. The grains flow around your fingers with relative ease. Now imagine that sand is slightly damp. It holds its shape better. The particles stick together. This stickiness is called cohesion. It is caused by the thin films of water that cling to each grain of soil, binding them together through surface tension. The more clay and water in the soil, the greater the cohesion. This force makes the ground resist being broken apart. It is one of the first major obstacles the mole must overcome with every single push. But cohesion is only part of the story. The particles in the soil are also pressed together by the immense weight of everything above them. This is called compaction. Every foot of earth exerts pressure on the layer below it. The deeper you go, the more compacted the soil becomes, with fewer air pockets and a denser structure. This compaction dramatically increases the friction between particles. For the mole, digging deeper means fighting against an ever-increasing force that tries to hold the earth in place, a silent and constant resistance that saps energy with every inch gained. So, the ground is not just dirt. It is a granular material with its own internal physics. It has cohesion holding it together, and compaction squeezing it tight. A mole doesn't just dig a hole, it must mechanically fracture this structured material. It has to break the bonds of cohesion and then physically displace the compacted grains. This process requires an enormous amount of energy. The mole is essentially a tiny demolition machine, engineered to break down and move a substance that, for its scale, is as formidable as concrete is to us. Understanding this challenge is the first step to unlocking its secrets. How do we measure the challenge the mole faces? We can use the language of physics. The key concept is pressure. Pressure is simply the amount of force applied over a certain area. P equals F divided by A, P equals F/A. Think of it this way. Lying on a single nail would be incredibly painful. Lying on a bed of thousands of nails is possible, because the same force is spread out over a much larger area. The pressure at any single point is much lower. The mole must contend with pressure from the surrounding soil, known as confining pressure. Example, a square meter of typical topsoil, 1 foot deep. That can weigh around 100 kilograms. This weight creates pressure on anything below. If a mole is digging a tunnel just below the surface, the soil above is constantly pushing down. To keep its tunnel from collapsing, the mole must withstand that pressure. And to move forward, it must exert even greater pressure to push soil out of its way. It's a constant, invisible battle against the weight of the world. From old field logs and laboratory experiments, scientists have measured these forces directly. In the early 20th century, researchers devised simple instruments called penetrometers to test soil resistance. These devices measure the force required to push a cone-shaped rod into the ground. A study from the 1950s, pushing a 1 square centimeter probe into damp loam required about 50 newtons. That's roughly the force needed to lift a 5-kilogram weight. The mole must generate that kind of force, relative to its size, continuously. This brings us to the mole's brilliant strategy. Remember its wide, spade-like paws. They are not just for scooping. They have a large surface area. By applying its muscular force over this broad area, the mole can exert significant pressure on the soil face. At the same time, its sharp, pointed claws work on a different principle. They concentrate force onto a very small area. That concentrated force fractures hard clumps of earth and severs roots. The mole uses both sides of the pressure equation to its advantage. Broad paws to push, sharp claws to break. Moving earth is hard work and, All work requires energy. In physics, work is calculated as the force applied to an object multiplied by the distance it moves. For a mole, this means every centimeter of tunnel represents a specific energy cost. This cost is not fixed. It changes dramatically depending on the type of soil it is digging through. A mole tunneling through loose, sandy soil might as well be on holiday compared to one fighting its way through dense, wet clay. The energy expenditure can vary by a factor of 10 or even more. Early naturalists documented this by simply observing where moles were most active. Archival maps from ecological surveys often show mole populations concentrated in areas with loamy soils, which offer a perfect balance. They are soft enough to dig through without extreme effort, but cohesive enough to hold a tunnel's shape without collapsing immediately. These old maps are, in effect, energy cost charts for moles. They show us that moles are not just digging randomly. They are making calculated decisions based on the physical properties of the ground, seeking the path of least resistance. We can quantify this energy cost. Laboratory studies have measured the oxygen consumption of moles while they are digging in different materials. By placing a mole in a sealed chamber with a container of soil, called a respirometer, scientists can track how much oxygen it uses. The results are astonishing. The energy cost of burrowing for a mole can be anywhere from 360 to 3,400 times more expensive than moving the same distance on the surface. This is one of the highest energy costs for locomotion ever measured in the animal kingdom. It is a lifestyle that requires an almost impossibly efficient engine. This immense energy demand dictates the mole's entire life. It must eat voraciously, consuming nearly its own body weight in earthworms and insects each day, just to fuel its endless excavation. It cannot afford to waste a single movement. Every aspect of its body, from its paddle-like hands to the way it breathes, must be optimized for peak efficiency. The high cost of digging is the ultimate selective pressure that has shaped the mole into the subterranean marvel it is today. It is a creature born from the unyielding physics of the earth itself. If the soil is a formidable opponent, then the mole's body is a perfectly engineered machine designed to conquer it. To see how, we must look beyond its velvety fur and view it as a collection of mechanical parts. The most obvious are its forelimbs. These are not legs for walking, they are shovels. Shovels powered by an engine of muscle and bone. The entire front half of the mole's body is a dedicated excavation unit. It is built not for speed or agility on the surface, but for pure, brute force power underground. Let's examine the anatomy. The mole's forepaws are immense in proportion to its body, equipped with 5 long, sharp claws. But the real secret lies in how they are attached. The shoulder blades are long and narrow. The humerus, the upper arm bone, is incredibly short and wide. This entire assembly is rotated, so the palms of the hands face permanently outwards. This orientation is crucial. It means the mole doesn't scratch at the dirt in front of it. Instead, it performs a powerful breaststroke motion, carving away the soil, shoving it to the sides, shoving it to the back, clearing a path forward with each cycle. This design transforms the mole's body into a living piston. The primary muscles involved are the pectorals, the large chest muscles, massively developed in the mole. These muscles pull the forelimbs inward and backward with tremendous force. We can see this machine in action using X-ray cinematography. This technology allows us to peer inside the mole as it digs, revealing the intricate dance of its skeleton. The footage shows how the clavicle, or collarbone, provides a rigid anchor against the sternum. The humerus bone rotates almost 180 degrees with each stroke, a range of motion unheard of in most mammals. It is a beautiful, powerful, and highly specialized system. The mole's body is not just adapted for digging. It is a digging machine, a biological marvel of mechanical engineering perfected over millions of years. Beyond the obvious power of its limbs and the sensitivity of its nose, the mole possesses a suite of more subtle, yet equally vital, adaptations. Let's look at its mouth. Digging is a gritty business, and soil particles inevitably get everywhere, including in the mole's food. This constant intake of abrasive material would quickly wear down the teeth of most animals. If a mole's teeth were to wear out, it would be unable to eat and would starve. The mole's solution is found in the complex structure of its teeth. The mole's teeth, particularly its molars, have a complex, multi-cusped shape. As the teeth wear down, new cutting surfaces are exposed, maintaining their effectiveness for much longer. Another hidden tool is the mole's fur. It is short, dense, and velvety, with no particular grain or direction. You can brush it smoothly forwards or backwards. This is not for comfort, it is a solution to a physical problem. The mole's unique pile allows it to move in reverse just as easily as it moves forward, reducing drag and saving precious energy. Digging is incredibly hard work, and it happens in a place with very little air. As the mole breathes, it uses up the available oxygen and releases carbon dioxide. Oxygen levels would cause a human to lose consciousness. So how does the mole not only survive, but actively work in these conditions? The secret lies not in its lungs, but in its blood. Red blood cells are packed with a special type of hemoglobin. This mole-specific hemoglobin has a much lower affinity for oxygen than ours. The hemoglobin can release its oxygen cargo very easily to the mole's hardworking muscles, even when oxygen levels in the blood are already low. The other problem is the buildup of carbon dioxide. However, the mole's unique hemoglobin is incredibly tolerant of acidity. This lets the mole rebreathe tunnel air for extended periods. Like a deep-sea diver with a rebreather system, except the rebreather is built into its bloodstream. To truly test and understand the physics of the mole's efficiency, we can now bring the mole and its environment into the digital world. Using powerful computers, scientists can create complex particle simulations. These simulations model the soil as millions of individual grains. We can program them to stick together, cohesion, and to press down on each other, compaction. Into this digital soil, we can introduce a virtual mole, build a 3D model of its skeleton and its musculature, program it to move with the same powerful breaststroke motion as seen in X-ray videos. Now watch, the simulation reveals forces at incredible detail. See soil particles flowing around the mole's paws. Measure stress on its virtual skeleton as it digs. Visualize the areas of highest pressure. These simulations let us ask impossible what-if questions. Remove the extra os falciforme bone from the virtual wrist and see how much less soil it moves per stroke. The ultimate goal of studying the mole's engineering is to build something new. Let's take the lessons we have learned and design a concept for a robotic digger, a molebot. This small, autonomous robot would be designed for tasks where conventional digging is difficult or dangerous, laying small underground cables, search and rescue in collapsed structures, scientific exploration on other planets. The design would be a direct translation of the mole's biology into mechanics, propelled by two powerful mole-inspired forelimbs, wide spade-like paws, leading edges fitted with hardened claw-like tips to fracture compacted material, fracturing and displacing ground in a single efficient motion. A drill needs about 100 joules to displace a liter of soil. Using the mole's leverage principle, the molebot might need only 70 joules. That's a 30% energy saving. Longer battery life, greater range, nose cone packed with sensors, vibration detectors, contact sensors, ground-penetrating radar. This is not science fiction. It's the practical application of millions of years of evolution. A better way to build. We began our journey with a simple question. How can a small, unassuming animal conquer the immense physical challenge of the subterranean world? We have traveled from the physics of soil to the intricacies of biomechanics. The answer lies in a suite of brilliant solutions, a masterclass in natural engineering. The story of the mole is a powerful reminder that some of nature's most extraordinary marvels are hidden just beneath our feet, working tirelessly in the dark, silent world below. In a moment, it will be gone again, leaving behind only a small mound of soil as evidence of its immense power and industry. A silent testament to the superpowered mole you never knew existed. If you have enjoyed this journey, please support our channel. Like this video and subscribe to join us as we continue to explore the hidden physics of nature. There is always more to discover, just beneath the surface. Thank you for watching.